Olá, pessoal. Hoje daremos mais uma reunião de grupo, tá? O Álvaro vai começar a apresentação. Hoje, dessa vez, começaremos com a pós e depois com a graduação, tá? Pronto, vai lá, Álvaro. Agora seria bom que Maurício fizesse a cobaia aqui para ele ficar mostrando o que o Álvaro vai apresentar. Então.
Seria bom se desse para colocar a tela, né?
Agora abre lá. Quer dizer, a gente só está vendo o que o pessoal está vendo, eles não precisam ver isso, né?
Esse porque, por exemplo, a gente pode...
Share screen. Não, agora você vai fazer o seguinte, peraí, deixa eu me mostrar. Você vai clicar nesse botãozinho aqui, ó. Aqui. Peraí. Peraí. Como é que eu cancelo esse aqui, hein?
Uma câmera não, tá com a câmera do laptop.
Pronto.
Ainda.
Dê uma olhada agora no YouTube para ver.
Mas, professor, tá usando a câmera do computador, essa não?
Não, tá usando essa.
Essa tá usando?
Não, tá usando de cá, ó.
Do computador.
Tá usando no computador?
Sim.
Tá. Então veja aí, eu tenho que usar a...
Mas um noite,
Tá vendo?
Realmente, tá diferente.
E aí?
E aí que eu não sei desse bota.
Peraí. Deixa eu fazer aqui, settings. Câmera.
Aqui embaixo.
Aí bota aqui. Aí tu vai ver a calça do Johan. Pronto. Beleza.
Se não der certo como físico,
Como
vai
que é?
ser como,
Pronto, vamos lá.
eu sei lá, cara. Tu nem entendeu, né?
Não, tu fala...
Deixa eu ver aqui.
Deixa eu ver qual é a tela que tá mostrando aqui. Ah, peraí, ele tá colocando...
Tá certo, tá aparecendo a tela lá normalzinho e tá...
Não, mas não tá aparecendo a tela.
Tá,
aqui, né?
não, tá sim, eu tô vendo aqui, ó.
Não, pô.
O que tu quer ver? Ah, sim, essa tu
É
bota
de
lá.
lá.
Tá
É isso que... Mas aqui não vai aparecer?
Vai, rapaz.
Ah, tô perguntando.
O Farinal tá olhando, bicho.
Tá vendo?
É porque eu tô atrasado aqui.
Ah, tá com delay.
Olha, tá aparecendo. E tá mostrando o Johan mostrando o quadro ali, todinho.
Pronto, aí tá beleza.
Aí quer ver? Vamos ver o cabelo da sala.
Aí tá.
Olha, tá mostrando o cabelo da Sara.
Então beleza.
Beleza.
Yeah, for instance. So, I guess everybody's here.
Okay.
Okay. So, since we are beginning with the postgrad meeting first, I'll start talking about this paper. Well, I don't know if which is called the exact tree level calculation of the dark photo production in high energy electron scattering SPSR SPS. Basically, this paper is about, well, the authors of this paper, they have the goal of trying to calculate and provide some limits over the relationship between the kinetic mixing of this dark photon and the standard model photon as a function of the mass of the dark photon, okay? That's the main goal of the paper. However, they are also trying to analyze the difference between two different approaches to calculate these limits, which are, the first way that you can calculate this is by as exact tree level. That's the first way to calculate this. So you have the cross sections of this production, which, by the way, is this process right here. Where it's interesting. It's best just to say right first. This is not the Z boson, okay? This is just a nuclei with Z as atomic number, okay? So this is the process of interest. You have at the beginning a beam of electrons, and this beam of electrons is scattered into a nuclei. And this scattering of these electrons produces the same from the beginning, also a dark photon, which in order to kind of show you guys more or less how this will happen, I will write a diagram here, which will be something like this. You have the electron, and you have this nuclei, okay? And then they share a mediator, which in this case will be a photon. And this will produce the dark photon. So this is the diagram of interest, where they found still an electron and the nuclei in the final state. That's the process of interest. So the authors in this paper try to calculate these two ways. The first one, as I already said, is this guy here. And the second one is an approximation, which is called the improved Williams approximation. The reason why they try to look for this, because this approximation here, it's way faster to be calculated, because this basically what this approximation does is that it reduces the number of integrals that you have to calculate. Then you have to bear in mind that you're not calculating just once. You need to calculate for a range of dark matter masses. So in the end, you might have like thousands of integrals that you have to calculate, both at the same time. So this approximation here reduces a lot of the time of calculation, okay? And so the main goal of this paper is like, they want to compare if using this method have some big difference. They want to see whether it is a good approximation or not. So, Sarah, can you just, yes, go to the, no,
This.
the paper. Go to the
Okay,
paper.
right.
Yes. Can you go to the image, please? Let me just, that's faster.
The question.
So this here is the comparison between those two plots. Our comparisons between the calculation of this differential cross-section as a function of energy, okay? Well, function of the ratio of energy of the dark, this X factor is the energy of the dark photon over the initial energy of the electron, okay? So this is a plot of the differential cross-section as a function of this factor X. And then they are using two different colors. The color in red represents an older paper, which was produced in, correct me if I'm wrong, 2013. And the black lines represent the calculation from this paper, okay? And as you can see, there is a nice level of equivalence between those two measurements, okay? And here in the right side, they compare the ratio between these two differential cross-sections. And as you can see, there is a very considerable coincidence between those two results, since it goes, one, it will be the case where they're both equal, okay? It will be 1. However, you can see there's 0.9. So there is a nice level of concordance, well, between those two methods of calculation, okay? So, going on. Another result of this paper, which is quite interesting, is the result of this cross-section, differential cross-section, when compared with GN4. I don't know if you guys are familiar with, but GN4 is a software where you can produce your own experiment in your PC. So you can say, well, we have this kind of target, we have this kind of detectors, so you can do all of that with GN4. And so they compare the results that they had considering the first method, which has actually level calculation. And as you can see, in the case of the mass of the dark photon equals 0, they get pretty much the same results. So this calculation is still a very good approximation. And then they are starting to consider different cases of mass of the dark photon. And as you can see, there is a difference in the differential cross-section, which is caused by the dark photon. Okay, and the other result, since I need to be faster, here, there's a lot of calculations here in the middle, and I'm not going to talk about that. And then here we have the comparison. This is actually the main result of the paper, which is the comparison between those two methods that I said, talk about in the beginning. And it's a very interesting thing because depending on the mass of the dark photon, those two methods, they start to fall apart. Because especially in the case of the mass of the dark photon, of the order of 100 MeV, as you can see, depending on the energy of the electron beam, the difference can go a factor of 2.7. So,
Are you saying that if the two methods are equal, all the lines have to be straight? Yes?
yes, it should be, if they are equal.
All right, all right.
But as I said, there is a bit dependence on the mass of the dark photon. So this means that those two methods, they should be more or less the same in a region between 5 MeV until 20 MeV, I guess. You can say that they are well, it's a bit forced a little bit, but they are in this region right here. So you can more or less say that they have the same results, okay? Which is very nice, since this guy is way faster than the first one. So that's good.
But it's very stringent,
Yes,
the mass limit.
yeah, that's a problem.
And between 5 and 10 MeV is only?
Yeah, that's actually a very interesting case because another dependency which is interesting here is the dependence of the energy of the initial beam. Because as you can see, as the beam gets more energetic, those two, they start to get a little bit closer. So if you have a system which has initial energy of 100 GeV, this gets a little bit better. But you can also use this fact that you have here as kind of a correction factor, perhaps. That's one interpretation that you can do, right? And so let me go to the last paper. This is a very interesting result. Well, I'm going to talk about this. This is an interesting result which compares the number of signal counts as a function of normalized by 1 GeV. And as you can see, the dotted lines is the line considered the Williams approximation, and the solid lines represent the exact calculation. And as you can see, there are a few differences between them, which is what?
Because I and you have a fight between exact calculations and computer calculations.
Oh.
And I prefer two expressions of the things.
Well, it's a question of time, right? You can't always spend a lot of time doing exact calculations. So computers are good things. So let's the final result here, this is actually the most important result in the paper, even though I say that about 3 times. And this is the result where they predict the sensitivity of this experiment, which is called NA64, which is also now it's experiment because this paper is from 2017, the end of 2017. This experiment already exists right now. And here they predict the sensitivity of this experiment as in putting limits on the kinetic mixing, which is represented by this epsilon, as a function of the mass of the dark photon. And as you can see, it is a pretty nice limit since it's the order of 10⁻⁵. And then that's the main result of the paper, which is a pretty nice paper to read. And I hope that I gave you guys at least a sense of what's going on with this paper. And that's it. I don't know if you guys have any questions.
I don't know, but you mentioned that
Right. What is that for? So the interaction Lagrangian is given by this. That's the Lagrangian of the interaction.
It's some kind of suppress factor.
Yes, since this mixing comes from the addition of another symmetry to the model. So
It's a U1, another U1.
could be another U1. I'm not quite sure if it needs to be a because, for example, so I'm not pretty sure if it needs to be
Yes,
necessary.
because
this model
in
is-
a paper that I'm reading,
Mhm.
they
Yeah, but usually they use a
they
U1.
use another U1, a
Yes.
B, a B minus L,
Mhm.
and the same current in the Lagrangian.
Yes, that's the main way that the dark photon is introduced in the models. They consider a new, for example, you have the standard model, which is this SU2, U1, and then they add another U1. And then since those two guys are from similar groups, they mix. And the mixing of these two groups produces an interaction term like this. And so that's the usual way. But I think that if you have another, for example, a left-right model where you have another SU2 group, you also have another neutral gauge boson. So it should mix as well. So it's not limited to only to U1. It's a bit more general in this case. Any other questions? Okay, so let's now I'm gonna
Thank
host.
you, Álvaro.
Oh, thank you. Então, mudando para o português agora, vamos fazer a apresentação da graduação, né? Quem agora vai apresentar?
Sou eu.
Pronto.
Teria como mandar os detalhes para você por e-mail?
Tem sim, pode mandar.
Vou deixar assim,
Uhum.
para que a gente não olhe o e-mail.
Fiquei terminando a reunião só de pós-graduação.
Ele vai enviar tudo.
Tentei finalizar aqui o stream.
Então, acho que é aí.
Precisa dar até e-mail, não, Álvaro, primeiro.
Oi.
Ah, tá.
Eu acho que é aqui. Não sei.
Sim, né?
Acho que é.
Qual que é?
Acho que é aqui.
É porque eu acho que... Deixa eu remover isso. Acho que agora tá tranquilo.
Mas tá ainda online, né?
Então, peraí, deixa eu tirar só aqui rapidinho.
Pronto, tem um.
Ele tá me fazendo de otário aqui. Coisa rápida. Pronto, o e-mail é Álvaro.
Não mexe no cabo.
Começou.
Já falou.
Continua o stream.
Será que é?
Eu acho.
porque recebi fotos também.
Oi, pessoal, desculpa a demora, mas vamos começar agora aqui a apresentação da graduação, tá? Tivemos uns pequenos problemas aqui técnicos e já vamos começar aqui, tá bom?
700 pessoas online, né?
Ficou a boa apresentação. Bom,
Vai sentar, não?
Certo.
Okay, so I'll start. Good afternoon, everyone. My name is Michael, and I'll be presenting about the ebook Cosmos. But I actually talked to a professor, and I will try to bring up a little bit of Little's introduction to cosmology. It is just that you guys probably know all the subject that I'll be covering. It's just that I joined the group a little late. I think it was November, December of last year, so I'll be covering this one today. And I divided it in two parts because my presentation has two parts, which is one and another one in 2 or 3 weeks. I don't remember pretty well. And the topics I'll be covering will be main ideas of general relativity, geometry, universe and Einstein's mistake, universe expansion, and Hobos Law. Okay. First of all, when we are in high school, the first idea that we have of gravity knowledge itself is when we use the Newton's experiment, in which he is sitting below a tree, and then an apple falls on his head, and then he starts wondering, okay, if I jump, I'll come back to the ground, and the same thing happens to this apple and every object that is on this planet. So maybe there is a force trying to keep everything together and pull it to the center of this planet, in which he decided to call it gravity. And he treated it as a force. And we also, especially when we are in physics introduction, like introduction to mechanics, we always take time as like this rig in which we have those intervals equally spreading like 1 second, 2 seconds, 3 seconds. And in high school, that's basically the idea that we have of physics, of time and gravity. Okay, but I suddenly realized that, for instance, when someone is approaching the speed of light, or some object is approaching the speed of light, things around this object start to change. And that's because, and which led him to 2 fundamental conclusions. The first one is that in the vacuum, the speed of light is a constant and no object can travel faster than it. And the second fundamental conclusion of Einstein's theory is that gravity is a distortion of space-time, not a force as we used to in high school. Okay. I remember also when I was in high school and I asked myself, and I was Googling everything, and then I remembered that I was like, okay, but what's the size of the universe? It's like 1 galaxy, 3 galaxies, 100 galaxies. And apparently the observable universe has approximately 93 billion years light diameter. But the universe is approximately 13.7 billion years old. And which you may be wondering, okay, is the universe, are the galaxies going away from each other faster than the speed of light? Are they actually moving faster than the speed of light? But actually, speed of light is the fastest light that we have for an object. So how come a galaxy go faster than this? But what happened is that what Einstein said is no object, no particle, no nothing can go faster than the speed of light. But what is happening here is that the space-time is expanding, not that the galaxies are actually traveling, but it's the space-time between galaxies.
So I have a joke for you. What's the size of the universe?
What's the size of the universe?
Yes.
Oh.
It was your first question.
Okay, here it says the observable universe has 93 billion years light diameter.
It's a joking because if the universe is flat, as we think they are, it's infinite. Because flat geometry, it's infinite.
I see.
And we think that it's flat, but we can see all because of the light cone.
I see.
But
okay.
It's a funny joke because there are very difference between the observable universe and the size of the universe.
The actual universe.
So has a lot of things in the universe that we never will be able to see. So remember this.
Okay, thank you. And we also get, okay, the next topic that I'll be covering is actually Hobos Law. It's actually very quick. It's just that the basic idea that we have kinematic and introduction to mechanics. And I think this is the first equation that we see in mechanics and physics in general. We have, okay, space is equals initial space plus velocity times time. And we also usually take, for instance, that the initial space equals 0, which leads us to this final one, v equals space divided by time. And what happened here with the Hobos law is that, okay, let's just call 1 divided by time by h, and let's just call it related to Hubble. So the final equation is v equals h times the space, in which this would be the Hubble's constant. And actually, the Hubble parameter. And actually, physicists, they do not agree with the value of this Hubble parameter. If you take a look at some articles, they will say, okay, this is definitely 68. No, this is 74. This is 70, but it's around this 70. But the main idea is that if you have one different, like 68 from 69, it's a big difference for physicists. It means that something is missing. But yeah, that's the basic idea that we have of Hubble law. And actually, we have a graphic here in which on the x coordinate we have the distance, and in the y coordinates we have the velocity. And just like confirming what we were saying is that the further the galaxy is from us, the faster it's moving away from us. Again, not because the galaxy itself is moving fast, it's just that space-time between galaxies is expanding. Okay. Last but not least, we're gonna talk about the geometry of the universe. I'm not gonna lie, I tried to see the details of creating my equation, but it's just so long and it involves so many subjects that I still don't know. I'm still on the third semester of graduation, so I don't know that much about it. I just know that it's related to tensors and all this difficult stuff. But actually, what we want from the final equation is that to get there, we actually need to know three properties of the universe, in which we call isotropy and homogeneity. We say that the universe looks the same in each point, and the universe looks the same in all directions when you take a look at the universe macroscopically. That means, I think the analogy that most of people they do about it is when, like, okay, you're in the middle of the forest, and the only thing you see around you are trees. You know that the tree on your left is different from the tree on your right, but if you take a look at microscopically, if you take a quick view, you actually think that they all look the same. So we have those two properties of the universe, isotropy and homogeneity. What do we want from here to the final freedom equation is actually the value of k. Because if you take a look at this basically numbers, h pi d divided by 3, what do we want from here is actually the k. And we have three possible values for this k. We have k is bigger than 0, which would lead us to the conclusion that the universe is spherical. We have the k equals 0, which would lead us to the conclusion, okay, if it's 0 divided by h, we cut this part and we only have the 1 in the left. Well, we basically have the flat universe. And if the k is below 0, we have a hyperbolic universe, just like we see in those three pictures here. Okay, but what is the shape of the universe really looks like? There is a way of trying to find this in which you taken the principle that we just talked about, the isotropy and the homogeneity. The universe is all the same, looks the same in each point, in each direction. So I can get three random points on the universe and try to draw a triangle and then sum the angles inside of this triangle. If the universe is an open universe, then the sum of the triangles will lead it to below 180. If the universe is flat, it will add up to exactly 180 degrees. And if it's a closed universe, like a sphere, it would lead us to the sum adding up to more than 180. But all of the computational physics problems that we have so far have showed us that the sum of three random spots on the universe is exactly 180 degrees.
But this is the reason? that you will know the universe is flat?
Well, actually, this is the result that the physical computational research showed us so far. So we think that the universe is flat. It's not like, okay, this is
No,
it.
it's because the CMB, the cosmic background radiation. This
Radiation.
tells us the universe is flat.
I see. Okay.
Because you can put the parameters of the theory in change and compare with the spectrum of the CMB, and the only possibility that fit experimental data with the calculation is for k equal to 0.
Oh, okay,
This is
yeah.
the hammer that the
hammer.
universe is flat.
Oh, I see. Actually, this was the next chapter in Lino that
I'm
I
so
was
sorry.
that I was going to. No, but thank you very much.
I'm so sorry.
This is very useful. I'm actually looking forward. Thank you. Thank you. So this will lead us to the conclusion that we just said here. Einstein's contribution to understanding the universe, especially when you take the speed of light as a constant in the vacuum, the homogeneity and isotropy of the universe. Time is not absolute and gravity is not a force. We also take gravity as a distortion of space-time. The other one is what the shape of the universe looks like, what David here just said. And we have the Hobos Law and its role to an expanding universe. Thank you very much. This is it. Should I go now?
Yes.
So, any questions?
No one questions? I don't believe it. Guys, I don't believe it. It's a so very interesting point. Let's go, don't be shy.
Okay, I have not much of a question, but a comment. Can you go back to the slide where
Okay.
you were talking about the Hubble law?
Oh, the Hubble Law? Okay.
Yes.
Okay. This one here?
Yes, this one. There you say, let's say that 1 over t is equal h.
Can you
You need to
repeat?
be careful with that, okay? If you're talking about something like the dimension, you can say that. The dimension of h is the inverse of time. But that is not true usually, because
Okay.
h is the expansion rate, and it depends of the content of your universe. So if you have a universe that is mostly made of radiation, the dependence of t can be different. If only formed by matter, it can be different as well. So, and an interesting test that you can do is that you know the Hubble rate, and you want to know the time of the universe only using that equation. You will see that it gives the wrong result. So it's very important to be quite clear that even though that makes sense in a dimensional way, in the stricter sense, it's not true.
Okay, I see it.
This is because this way to think is, for example, for only one kind of matter in the universe.
Yeah.
But our universe, I don't remember the number exactly, but 50,000 years after the Big Bang, the universe was dominated by radiation. For 50,000 years to 10 billion years, so what this big difference? It was matter domination, and the 10 billion year to today is the vacuum that dominates the energy of the universe. So when you put this in the Friedman equations, the time is very complicated to find. It's not so very complicated because we made the computer do the math for us.
Okay.
But this is a first order approximation of this. There are corrections.
I see.
And this way to express the Rumble law it's a Rumble formula maybe, but it's a name that the community likes. All right. And it's because this is a very, very no long distance galaxies, because it's changed a lot when you consider thousands and thousands of the megaparsecs of distance. Have a lot of terms that they are not subdominant. They are not subdominant. They import, but for The next galaxy, the local group is great.
Okay, actually, I have a question for you.
Yes, you can.
That would be related to why this is not 100% a straight line.
Yes, because look at here. You are talking about megaparsec distance. They are the Hubble velocity is the velocity between the expansion, the velocity due the expansion, but there are two a peculiar velocity because the galaxies is suffering gravitational interaction between each other. So, but when you're far away, here is great. But when you're far away, the dispersion is big better because here the Hubble law it's not true. In that way, there are corrections that are very important, but the Hubble law is approximating to short distance only. In that way that you show for us. If you want a full plot of this distribution, you need computer because you need to put the peculiar velocity between the galaxies, the clusters, I think, the mega clusters, and the expansion. This is hard to do analytically, but it's for very, very fast, these very, very far galaxies, we don't care because the Hubble velocity wins. But for next, no, it's not because I'm not talking about that expression for the Hubble.
Oh, I see.
Yes, understood? Mm-hmm. I'm talking about the real expression of the Hubble law.
So, any further questions? Yes, you can say.
Why the Hubble law doesn't apply to very distant galaxies?
It's easy to understand because you don't want to answer.
Just state it. Well, you know the answer of the question.
I actually don't know.
So you can explain.
It's easy to understand because when you talk about distance in the universe, you are talking about the dynamic of the whole kind of matter energy of the universe. The Hubble law approved in that way only for a local group. You can do this analytically. You can do that. You will find some kind of, remember the name, common distance, and you find that common distance it's equal to V, another expression, ED. No, in time. So the Hubble law is this first one. Can you understand what I'm saying? The full calculation I don't remember well because I need hours here to show you. But the Hubble law have to be in the limit that these other contributions are suppressed. And you have distance, velocity, and time.
Straight line.
Straight line.
So basically, that's approximation for a small region. Okay, it's not valid for long distances. That's basically that.
And the universe expanding, accelerating. Is a de Sitter space.
Oh boy!
Huh?
Don't start with that.
Is a exponential factor.
So it's like if it's accelerated, it should be a parabola.
No, it's literally exponential curve.
Yeah.
This happy. The form factor are exponential. exponential to lambda T. The vacuum energy, cosmological constant, the time, so explode. So the universe the galaxies in the universe will be so far that in the future will be impossible to receive light the one for other, and the universe will be black. And
faster than light.
yes, it's possible they expand faster than light, but this don't mean that any two convolving observers can communicate each other faster than light. Only the universe are stressing so fast that we cannot communicate each other anymore.
Okay. Further questions? No? Okay, thank you again for the presentation. So,
Tem outro? Ah, sim. Ok.
ok.
Porque ele falou que tinha outra pessoa que ia apresentar, né?
Não tem outra pessoa para apresentar?
Não, tem mais não. A pessoa cancelou.
Tá, pode finalizar.
So,
Tem alguém online ainda?
okay. We don't have any more presentations.
Maurício, assistindo.
Não, bom, como não temos mais nenhuma apresentação, pessoal, então vamos finalizar aqui a reunião por aqui, tá bom? Muito obrigado a todos que estão assistindo e até a próxima.
Ninguém acha não, bicho.